Alright, so what reactions can I do with acid anhydrides? So let's start off by looking at what would happen if we took an acid anhydride and reacted with a chloride. So chloride's got electrons. One of the carbonyls wants them. Doesn't actually matter which side you use. Although if the anhydride is not symmetrical, then it will matter and it makes the reaction more complicated. However, in this case, I have a symmetrical anhydride. So the chloride comes into one side, pushes the electron pair out onto oxygen from one of the carbonyls. If you're protesting at this point, that's okay, and I'm actually glad that you are, but I'll walk through this reaction first, and then we'll talk about it some more. So at that point, now the O- can come back, reform the carbonyl, and you could have the carboxylate leave to make an acid halide plus a carboxylate. Now, if we go back and look at pKa's of our conjugate acids, the pK of this one's around 4 to 5. The pK of this one's around -7. So that makes this 10 to the 11, or 10 to the 12, times worse leaving group than chloride. So will this reaction occur? I guess you could say that it could occur. It's going to occur 10 to the 11 or 10 to the 12 times more in the opposite direction for every one time it occurs in the forward direction. So in the end, you cannot use an acid anhydride to make an acid chloride. It will not work. And we talked about that at the very beginning when I talked about the different reactivity of the derivatives. You can only make things that are less reactive than the starting material. So what can we do with an acid anhydride? Well, we could react with hydroxide in water or acid in water. Who has electrons? Who wants them? Hydroxide has electrons. Carbonyl wants them. Electron pair goes up from the carbonyl pi bond out onto oxygen to make our intermediate. The electron pair comes back to reform the carbonyl because we have a decent leaving group, and the carboxylate leaves. To make our carboxylic acid and our carboxylate. Again, look at pKa's. Here we have about 4 to 5, and here we have 15.7. Looking at the pKa of the conjugate acids. So what that means is that this is more stable by, again, about 10 to the 10 to 10 to the 11 times. More stable than hydroxide. So will this reaction occur? Absolutely. This one will occur. Again, you can do almost the same thing with an alkoxide, where the alkoxide will come in, attack the carbonyl, electron pair goes out onto oxygen, forms the intermediate. The intermediate, the electron pair comes back down to reform the carbonyl. We have a carboxylate as a decent leaving group to form our ester. And the carboxylate. And again, pKa's of the carboxylic acid, the conjugate acid of this, 4 to 5. pKa's of the conjugate acid here of the alcohol, 15 to 18, so in that range. So this one again is going to be 10 to the 10 times more stable. So this reaction will also occur very readily. We can do the same sort of thing with ethylamine. We actually need 2 equivalents of ethylamine to make this reaction occur. So we ask the same question that we always ask: who has electrons? Who wants them? The amine has an electron pair. Carbonyl carbon wants them. The electron pair moves out on carbonyl oxygen to form an intermediate. So with our intermediate, do we have a good leaving group? Yes. So the electron pair comes back down, reforms the carbonyl. This electron pair leaves for our carboxylate leaving group, giving our protonated form of our amide. That's why we need 2 equivalents of the ethylamine, because the second ethylamine will come along and deprotonate our amide to get rid of this positive charge. And again, you can look at what the byproducts are. The byproduct here is going to be the carboxylate anion. And now we can compare the carboxylate to the amine, and the carboxylate is going to be a more stable leaving group.